Hello, everybody. So my name is Christophe Tremblay with Analog Device. I am managing a secure products product line, so secure ICs, basically. And today I'm going to share with you the vision of security at the edge that we promote and that we believe in at Analog Devices. So first, IACS stands for Industrial Automated Control Systems. So first, I'm going to talk a little bit about the risks to which IACS are exposed to. I will then introduce a recent standard, which is IEC 6243. Then see how these standards impact the design of edge devices. And then we'll explain how Analog Devices can help the stakeholders reaching their objectives towards this standard. Okay. So let's start with the IACS at risk. Okay, so here we are seeing conflicting trends. So what I mean by conflicting trends is our trends that goes against each other. So first, if you look here, I'm sure you heard about Industry 4.0. One of the characteristics of Industry 4.0 is that we expect higher availability from the infrastructures. Like, for example, if you consider a critical infrastructure like a power distribution system or water treatment facility, Industry 4.0 calls for more limited number of downtimes. We want to avoid downtimes. We want the infrastructure to be highly available. Okay. At the same time, if we're talking Industry 4.0, it means that there is more connectivity, more devices talking to each other, and more digitalization. And as a consequence, this creates new opportunities for hackers. The more things are connected, the more opportunities you create for hackers. We say that typically you increase the attack surface. So that's the first trend on the left-hand side. On the right-hand side here, what we are seeing, I'm sure it will not be a surprise if I'm saying that the cyber attacks are getting more and more sophisticated, and also there are a growing number of these attacks. Okay? So one direction, you want the industry to be more available, more connected, and at the same time, you open the door to new attacks, and you see more occurrence of those attacks. In the middle here, what we've seen is that the adoption of security measures in industrial IoT has been so far very slow. Okay? I mean, cyber attacks are not new. They appeared like, let's say, maybe 10, 15 years ago. And still, there were not so many security measures implemented. Why is that? Is that so far, people were lacking a common reference. Okay, so if you are designing and manufacturing industrial equipment, you would be hesitant to implement security measures if you don't know what is expected and what are the right things to do. Okay? In general, your money and R&D resources are precious, and you want to invest them where you know it is useful. Okay? And so far, this hadn't happened. Okay. Luckily, now we have standardization. And the standardization results from an industry consensus. All stakeholders have been gathering and meeting to establish the standards, whether they were equipment makers or infrastructure users. Okay. So they established a common reference. And thanks to this, as a consequence, the implementation decisions were unlocked. Okay, so today, we are already seeing that standardization is solving or, let's say, limiting the hesitancy to implement security solutions and measures. Okay? Okay. So now we'll introduce the IEC 62443. So most people working in the industrial factory automation heard about these standards, but I wouldn't say that so many people master the standard. Okay, why is that? First, if we look at it, we can see that it addresses all levels of requirement. And that's definitely a strength for the standard. The upper part is about, general statement, like defining a common language for all stakeholders. Second level here deals with policies and procedures. Typically, here you would establish how to manage the maintenance, for example, of an industrial system securely. How you would train people, how people would themselves take individual security logins, how you implement security policies, password management, all of this. Third level is about the system architecture itself. I mean, how do we define a secure system as a whole? How do we establish the various system security levels? Okay. And at the bottom, we have what we call the component level. So a component in the context of IEC 62443 is something that is operating the IACS. It could be a piece of software, it could be a sensor, it could be an actuator or a programmable logic controller, for example. Okay? So interesting thing, the standard covers all levels, and that's definitely a strength. But unfortunately, there is a price to pay for that. The standard is 1,000 pages long, and it's actually very complex. It might be a disappointment for some people who would expect that the standard will tell them, hey, here you need to implement encrypted communication in that place. And somehow that will be easy. However, this is not the way the standard works. Actually, the standard calls for a risk analysis, okay? And once a risk analysis is conducted, and actually no one can do it on behalf of the implementer, then the standards explain to which requirement you should stick and how you should implement your measures based on this analysis. So typically, the complexity is that it is not a cookbook that will tell you exactly what to do at which levels, but it's rather a set of guidelines, good practices, and some references. Okay? Okay, so now how do we apply the standard to edge devices? As I said before, the standard is covering everything, all levels. But here we're going to talk about edge devices. As I said, at the bottom we have the component levels. Okay, so the edge devices would typically fall into the category of the component. Now, how to implement? The system level analysis here will tell us which target security levels we need for each type of equipment, depending also where it is used in the infrastructure. For example, if you consider a pressure sensor, you would not secure it the same way if you are in a food manufacturing facility, for example, or if you are in a nuclear plant. Okay? So typically, this is why the analysis here is really important. And for each part of the infrastructure, once the risk analysis is conducted, you get target security levels. Now, here, the component level of the standard will define which requirements apply for a given security level, and also how the requirements are mapped to specific types of equipment. For example, you would not implement encryption in the same way in a workstation, in a SCADA workstation, and in a PLC, for example, because you don't have the same resources, right? So typically, once this risk analysis is defined, you got the target security level, and then you're ready to design the components according to the guidelines of the standard. And here, this is typically where Analog Devices focused when we say that we secure devices at the edge. Okay, so now let's talk about those famous security levels. Nice thing about this standard is that it's fairly, the way that security levels are defined is fairly intuitive. So level 1 is accidental violations. They happen is that, someone, for example, inadvertently leaving its password exposed, for example, will be an unintentional violation, and that will be the first level. Doesn't mean that it is not harmful, But here we have to think that equipment, skill, motivation, or resources are close to 0. Level 2, you have a hacker. And in that case, you may assume that the hacker has some skills, can buy some equipment, and has some motivation to intentionally impact the IACS. Okay? Level 3 is going to be higher, is still intentional, but now we're talking about mafias, terrorist organization. And obviously, here they can invest more. Their level of motivation is higher because they have interest in seeing some infrastructure disrupted, for example. Okay, and the highest level is about government scale attacks, and we know that sometimes that happens. We have, unfortunately, wars today, and we know that cyber attacks are weapons that countries, nations would use. And here, of course, the level of resources, motivation, and skill is highest than ever. Okay? So these would be those levels described in the language of the standard. Okay? So unauthorized disclosure, but it's unintentional. Here, we're talking about something intentional, but with limited means and resources. Here, higher motivation and skills, and here, where we have to consider that means, I would not say are unlimited, but are very high. When it comes to invest $1 million for an attack, it's possible. Okay. So, cover now how we implement it. So how the standard will address the edge devices. So in general, the edge devices are embedded components, and I would say the traditional constraint for embedded devices are not new. We know them. Power, of course. In general, embedded device has limited power. Space is constrained. Obviously, if you're thinking about a small sensor, you want it to be small. You have very often limited computing power and cost. So traditional constraints for embedded devices. Now, if we put them in front of what the standard tells, and especially here we're talking about -4-2, which is related to component level implementation, we have common security constraints that will apply in general, and we have functional security requirement. So here, this is the way the standard architectures the requirement and sets the level of targeted resistance, sets the bar, let's say. So if we take the example of authentication, that will be a functional security requirement from the standard, and then it will give you a number of requirements related of this. And for example, if we're talking about authentication, it will tell you the required strength for public key authentication. The standard will also give the rationale behind. Okay, so we're not doing things for the sake of doing them. And then it will tell you also how the level applies to a given set of requirements. For example, if I'm taking authentication and if the strength of public key should be 256 bits, now I can say that starting from level 1, it could be a software library, but level 3, the standard will require hardware support for this. Okay. Then the standard will also set the devices, the requirements that are specific to the embedded devices. So a typical example will be physical tamper resistance, and level 4 would be that the device is able to notify a tamper type of attack. Okay, so again, now if this is a developer or designer eye, we have the traditional constraints and we have the requirements from the standard following this architecture. And of course, this is instantiated many times. Okay, so now how do we make it real? This is where an analog device can can help. So obviously, we are, in general, as a silicon vendor, as a silicon solution provider, we are very aware about all those constraints of power, space. So we do provide solution based on what we call secure authenticators. So what they are, some people call them also secure elements. So they are connected to an embedded processor, and they are here to bring the root of trust function. So typically, authentication, encryption, they enable user data storage and management of the device. To enable this, they embed all the fundamentals, secure key and data storage. They feature robust crypto engines, like, for example, when you compute crypto operations, you have to be resistant against external attacks, such as side channel attacks or fault attacks. And these are part of the foundation of our products. And last, you also need robust true random number generators. Now, how do we link those authenticators with the standard? So here, first, if you look at the high-level requirements, so there are a bunch of them, as I mentioned before, communication integrity, data confidentiality, certificate-based authentication, public key infrastructure. You will notice that here, in general, if we are talking about level 3 and 4, which are the highest level of the standard, then it becomes mandatory to have hardware-based security. And this is where we help and where it is compelling to use some security ICs. On the left-hand side, I have all the features, the function that are supported by the device, and you can see that we are able to map them to the standard in a very straightforward way. Okay, like for example, the standard calls for certificate-based authentication. We do have X.509 certification management in our IC. Same here, protection of audit information. We can add ECDSA. So we do have this rational table that will help the system, the component designers or the system developers to implement the security. And of course, this is also aligned with the security level of the standard. Okay. So this is an example of product of security IC, the MaxQ1065, which is, I would say, very well aligned to the requirement of the standard. Again, it is a kind of coprocessor, so it is connected to a host MCU through a SPI or I2C bus. It contains here ChipDNA, is a technology which belongs to the physical unclonable function family, and that is aiming at giving the highest level of protection of the keys and credentials that are stored into the IC. So typically reaching that level of protection is only possible if you use secure ICs. The device is predefined with security functions that you can call, like for example, you can call commands to execute authentication, attestation, or if you want to implement the TLS, Secure Communication Protocol, all the primitives are predefined here. So hardware crypto engines are here to provide the computing power that is not necessarily available in a small, tiny MCU that is commonly used in an edge device. So here, you're really buying the horsepower to compute cryptography. Okay. We said also that those systems were really power conscious. As you can see, we have very, very low current for shutdown mode, 100 nanoamp. And also because space is a constraint, for example, in sensors, it's packaged in a tiny 3 by 3 millimeter package with a 0.5 millimeter pitch. Okay. So our job again is to enable component designers and developers to implement. Is to enable them for an easy implementation of security. So coming with the parts, the physical chips, the secure authenticators, we have a complete software offer that runs on the host MCU. It is agnostic in terms of operating system, so it's a C open source middleware. All the developer has to do is to modify an adaptation layer to be able to talk to the driver already implemented in the system, and then the middleware provides a convenient API for the customer application. So altogether, the chip plus a software library running on the MCU enable an easy, convenient turnkey implementation of security in line with the standard following the guidelines. Okay. So that's a summary of the offer. Again, so we have a bunch of security ICs, so secure elements, secure authenticators, with all those characteristics. The host solution, so the software side. Okay. We also bring value-added services like key provisioning. We mentioned that there is a lot of cryptography involved. And when there is cryptography involved, then you want to be able to bring the keys to the device. So this is also a service that Analog Devices provides. We can program keys on behalf of our customers into the device, and we also have technical support.